Yes, I'll try and put the algorithm here, and then I'll kind of explain what's going on over on this side. Okay. Right, so what were we given? What's our setup? So we're given a coloring. I'll call it chi. The edge of the complete graph with red and blue. And let's assume that there is no red KK and no blue KL. Okay, and for us, L is at most K, and we think of L as being maybe, think of it as being L as being K over 100 or something. Okay. What else do we have? So we have two sets X and Y, subsets of the vertices, disjoint. Okay, think of it as being a random equipartition of the vertex set. And we're going to say that P at every given time, let's say P0 is the number of red edges, the density of red edges between X and Y. Okay, at time 0. Okay, if you like, you can think of these being X0 and Y0. I'm just going to call them X and Y. I'm going to update them in the algorithm. Okay, but these are our initial sets. Okay. We're also going to have a constant mu, which you can think of as being gamma, where gamma is L over K plus L. So actually, gamma won't play a part in the algorithm, but you can think of mu as being gamma, if you like. It'll play a role a little later. Okay. So we're given the setup, and we're going to repeat the following steps. Until the size of X is at most the Ramsey number KL to the 3/4. Okay. Actually, there's one extra condition that I'm ignoring. Officially, we also stop if the density of red edges gets super, 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 super low. But it will never happen, so let's not worry about it for now. We'll worry about it later in the analysis. Okay, so you can think of P as being a constant, and the density will always be a constant. It won't go much below the initial value. Actually, it's even a constant bigger than a half. Okay, so what's our aim? Our aim is to find, in this coloring, a big red book. Okay, so we start with some density. We're going to try and find this large red book. Okay, so these 5 steps. Please. Yeah, so the algorithm is going to work for every L at most K. It's going to give a book of a different size. Yeah. So when we deal later with L being very close to K, we're going to have to be we're going to think about what we're doing. But yeah, the algorithm works for every L at most K. Yeah, so L doesn't even need to be of order K. It can be much smaller as well. It's still the algorithm, but really, for this course, we're going to think of L as being of order K. Okay. In particular, mu will really be a constant, and L and K will be large. Okay, so L and K both are much bigger than 1, and this much bigger depends on things like mu. Okay, any constant I say, this depends on the constant. Okay, so step 1 is sorry, I'm going to introduce an epsilon. And I haven't told you what alpha is either, have I? So, sorry, let me do that as well. So I'm going to tell you what alpha is. Alpha of P is going to be epsilon P minus P0 plus 1 over K. Right, so P0 is our initial density of red edges between X and Y. P is our current density. So when P is bigger than P0, we're going to increase this guy. This is if P is at least P0 and alpha of p equals epsilon over k otherwise. Okay, so I'm only going to increase alpha when we're above p0. I'm not going to decrease it when it's below. Okay, so put a floor on what we allow. Okay, we'll see why later. And I show what epsilon is. So for us, epsilon will be k to the minus a quarter. We have a lot of flexibility. So it's really, I'm putting k to the minus some small number. But a quarter works, so why not? Okay? Okay. Okay, so the first step is degree regularization, which means remove from X all vertices with few red neighbors on the other side. So perhaps I should draw a picture somewhere. Okay, so what is our picture? Let's have the picture over here again. Oh, okay, this time, get it out of the way. Okay, so we have a set X, a set Y, and a set A, and a set B. A will be a red clique, and we'll send only red to both sides. B will be a blue clique, and we'll say and only blue to the left, but no restriction here. And our final red book will be A, Y. Okay? So this is the object we're looking for. A will end up with size t. And we'd like to make y as large as possible, large enough so that, so question mark, is this bigger than Ramsey r k minus t? I should say, sorry, get this right, k minus t L. Right, now we're doing off diagonal. Okay? Okay? Okay. Mm-hmm.
Why only the set y, but not x, cup y?
Right, so we're going to run the process until x is tiny. So you could include it. Yeah, we just don't care, yeah. Yeah, this thing will actually be is way, way, way bigger than x at the end. Yeah. Okay. With few red neighbors in y, so what does that mean? It means we replace x by the set of v in, or let's say x in x, such that the red neighborhood of x in y is at least p minus something times y. Okay, so let's try to think what we would want to put for the something. Okay, so let's remember what all these things were. So alpha is going to be basically the size of our steps. Let me just draw a picture over here. So we start at p0. 1 is up here somewhere. Right? So our first step, we start here. We're going to bet alpha in each step, which means if we take a red step, we're going to go down by alpha. Okay, which here is just epsilon over k. Then we take another red step, go down by alpha again. But then sometimes we're going to go up. Right? So, and as we go up, we should really think about this thing as happening at sort of different exponential levels. So instead of going down, if we go up by actually sort of many levels. So we go up to something that's like p0 plus some large constant times alpha, like alpha over mu or something. Right? And now our bet size is increasing. So now our single step size is now not alpha, it's now a bit bigger. It's alpha plus, it's got a bit bigger. Okay. So you should think about alpha as being sort of wherever we are, alpha is like the basic step size. And I said last time that we actually want here to have, we don't want to only remove things that are alpha smaller. because there's not going to be enough. Basically, then you could lose a lot of vertices in these steps without boosting your density much. So we need something here that's much bigger than alpha. So what's a convenient thing to take? Convenient thing to take is, well, it shouldn't be as much as alpha over epsilon. That's a bit too much. Do something in the middle. Let's take alpha over root epsilon. So epsilon to the minus a half times alpha times y. Okay, so our change in density we allow is just something that's much bigger than alpha and much smaller than alpha over epsilon, much smaller than 1 over k. Okay, this turns out to be the right sort of range. And within that, it doesn't really matter exactly what we do here. Okay, so that's a way of updating. Okay, so that was step 1. And now we go to step 2. Okay. 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 Yeah, I'm really not going to fit this algorithm on the board, am I? But we'll see how we do. Okay. So what is step 2? Step 2 is a big blue step.
Wait, but isn't it conditional on something happening? Isn't it step 2 conditional on something?
No, so we just do this.
And always do a big
And always do, no, sorry. Right, so the big blue step will be if something, then do something, otherwise do something else. Yeah. Yeah, so phrase it like that. So if there are at least Ramsey k L to the 2/3. Now, what is this? This is a number that's much smaller than L to the 3/4, right? Again, it doesn't really matter exactly what we put here, okay? There's a lot of flexibility, okay? And L to the 3/4 is a number that's much smaller than L, okay? Everything is just like, there's lots of space, okay? This many vertices, x in x, with many blue neighbors in x, many being measured by mu, okay, then we do the big blue step. Then, so let ST be a maximal or maximum size blue book with T big. So T should be at least, okay, so each vertex is going to cost us a factor of mu when we add it to B. Right? We're going to go into this blue neighborhood. And we're putting S in, so we should lose a factor of mu to the S. Okay, times the size of x. So we lose a tiny bit more over 2. Okay, so just some silly error term. And we don't care at all about this over 2. Okay? Then, and update as follows. So, A stays as it is. B gets S added to it. X becomes T. And Y stays as it is.
S and G are subsets of X.
Yeah, thank you. Thank you.
Of S.
So, I'm just going to take it to be maximum size. Right, so there's a choice here. So we will, in the end, find a guy with S of size L to the 1/4. But I'd like to write the algorithm just so it always works, without having to rely on any lemmas that we prove later. Yeah, so we're going to pick a big one. Yeah, so I'm going to move it up very slightly. Yeah, in X, thank you. In X. So S and T are both in X. Right. So maybe I'll draw it here. Here's X, here's S, here's T. S, T. Okay. And update. Right, so A goes to A. S is added to B. X is replaced by T. And Y stays the same. And go to step 1. Right? Okay? So, I claim that we're still in this situation. Right? We've added S to B. It's a clique. It's got this blue neighborhood as T. We've replaced X by T. So these are still all blue edges. These obviously still all red edges. Y didn't change. Okay? So we've maintained this picture, except it's made B bigger and X smaller. Okay? And by the correct ratio. Right?
We don't care about this error of on half or something in T because we just increased by a lot.
So the reason we don't care about this too is because these books are actually very large. Maximum size means sort of X max, S, right? So S. Yeah, by the size of S. Right? We're adding a lot of vertices at the same time to B. So we're not going to do very many of these steps. We're going to do L, because this is always at most L. This is at most K. We're going to do L steps at most. Each one's big. So little L, yeah, it's all fine. So this is not going to worry us. So factors of 2 to the little OK, we're not going to worry about. Right. If not, go to step 3. Yeah, and now I've run out of space. Okay, so we'll come back here. Yep.
The mute the S is big enough because the thing was that we wouldn't do a blue step for each vertex because we would lost a factor of 2 for the
Right. So the reason, so there's 2 different things here. So first, mu to the S is okay because we're adding S, the whole set S to B. So we're using a factor of mu for each vertex, which is what we want. So mu was chosen because we're willing to give that up in each blue step. Okay, or will be chosen, I guess. The reason that we want to take many blue steps at the same time, so this means the 2 doesn't matter. But more importantly, it means that this loss here doesn't matter. So I'm glad you asked just before I raised this. Right, so yeah, so what happens in the blue step? So what happens to P in particular in a blue step? We're replacing X by this essentially arbitrary subset of it. So what's our lower bound on P afterwards? The density of red edges between the new X and Y. It's just the Minderee condition. Right? This is our bound on the density on P, on the new P. And this is a lot. Right? It's a large number times alpha. I mean, it's actually like k to the 1/8 times alpha, right? It's huge. So we lost a lot. So we don't want to do too many of these things because each one is going to cause a big loss. Turns out we're going to be able to make these big enough so that this loss doesn't hurt us. Okay, make this so big, and we'll see in a minute that it's not difficult to do that. Make it so big that actually, even if you lose the maximum in all of these steps, it still is a rounding error. It's not a big deal. Okay. Okay, great. Okay, happy? I'm going to erase that and maybe I'll try and fit 2 steps in this one. We'll see. Yeah. Okay. It does matter. You must start with step 1 because if you don't do step 1 before step 2, you have no control at all over P afterwards. Yeah. So yeah, crucial that you do degree regularization first. Yeah. So we always do degree regularization and then one of the other 3 moves. Yeah. Okay. So we go to step 3. 3 is choose a central vertex. Vertex X And what properties do we want this x to have? So now we're going to have this little x, and we're going to decide based on his red and blue neighborhood here, and his red neighborhood here, whether we do a red step or a density boost step. So what properties do we want this guy to have? Well, okay, so let's recall what those two steps were. Okay, and he's going to have a red neighborhood over here as well. Okay, so to do a red step, we'd like three things to be true. We'd like this set to be big, we'd like this set to be big, and we'd like the density of edges across here to be at least p minus alpha.
Minus alpha p, right?
Alpha of p.
Whenever you write an alpha, should we understand?
Yeah, whenever I write it, you should understand it's using alpha of p. And yeah, unless I say something different. Yeah, I don't know how much of the calculations we're going to get around to. There are various times where it's annoying because this p and this p are going to be, well, sorry, this p and this p will be the same, but there'll be different p's, like, because it's changing over the steps. But anyway, it's just a silly bookkeeping. But anyway, so we need these three things. So, how big can we expect this to be? We want this to be big. What can we expect? Right, so yeah, so if we're thinking the diagonal case, then the density overall should be a half, so therefore this should be a half. But there's two things wrong with that. One is we're in the off-diagonal case. But secondly, and more importantly, we have no control over what's happened here. Right? We're in some crazy common neighborhood of the world. And the scary thing in all these Ramsey proofs is you go to some little corner of the world and maybe you lose complete control of your densities. Right? So we have to take the worst case here. So we cannot at all assume that it's nice. But
So someone said gamma.
I didn't hear. Shout, please. So what control do we have over the degrees, over the density in this?
You just said the degrees. We regularized the degrees before, right?
We regularize degrees across.
Oh, sorry.
Yeah, across, inside x. What control do we have over the degrees of vertices inside x? The clue is it's written on the board.
Oh, we just saw the size of the neighborhood, blue neighborhood of x.
Yeah, right. We just said, look, if there are lots and lots of vertices with high blue degree, then we wouldn't even have got here in the first place. Right? The fact that we arrived at step 3 means that there are very few, and notice this number is way smaller than this one. Right? There's only a tiny proportion of vertices that have degree at least mu. So it should be pretty easy to avoid them. Right? So let's avoid them. Let's pick an x that has a most mu times x blue neighbors. I'm not going to write times x, if that's okay. And therefore, at least 1 minus mu red neighbors. Okay. Okay, so I'll write that down first. Such that the number of blue neighbors of x in x is at most mu times x. Right? And therefore, red neighbors is 1 minus mu. Okay? Okay. Over here, we're happy because we have the min degree condition. So this is like at least p minus little o1, basically, times y. So, right, I erased it, but what do? We can guarantee p minus e to the minus a half times alpha. And remember, alpha is like 1 over k, and this is, yeah. So not quite true because alpha can be as big as, it can be as big as epsilon. So even then it's okay. Even then it's little o1. Okay. Okay, so it's always at most little o1. Right? And this little o1 is not going to worry us because what's the size of y going to be in the end? It's going to be like the product of these sort of p minus little o ones over all the steps. This is going to be like, so this is like this to the power k, like p0 to the power k. This is a constant, little o1. We get 2 to the little ok.
But this is like glossing over the fact that we're changing p.
Yeah, so this is going to be a lower bound.
Okay.
Yeah.
Oh, right,
So in fact, actually, all we need is this is at least p0 minus little o1. That's all we actually care about, right? And it will always be that, as we'll see later. Yeah. Yeah. So not yet proved, but it's going to be true. Okay. Yeah. So we're going to make sure p is always at least this, and we already know that this is little o1. Yeah. Okay. Okay. So the only thing left is the red density across. So if it's at least p minus alpha, we take a red step. If it's not, we want to take a density boost step. And that's going to be good for us because this set is small. Right? So the fact that this set is much bigger than this one is going to mean a small decrease here corresponds to a big increase here. Right? Okay. Okay, so, we're right. I glossed over something important. Right, which I'll probably write over there. So, why is it true that if you're smaller than p minus alpha between here and here, then you're bigger than p between here and here? Sorry? So it's really just counting edges, but we need to make p is not the density between x and this set here, right? It's the density between x and y. So we need to make sure when we choose x, the red neighborhood has density roughly p to x. Okay. No, central I just mean it's the vertex whose neighborhoods we're all like. It's the one that we're dealing with. But right, and what? And basically that the density of red edges between x and the red neighborhood of x in y divided by size of x, size of red neighborhood in say y. Okay, so the density of red edges should be not too small, at least p minus. I mean, we can basically get whatever we like because it's basically the ratio of these two numbers. Let's say 1 over k squared or something. So, or k to the 200 if you like. Yeah, whatever. Right. So the point is just that what's the ratio between this number and this number? Right? Well, if we remember just our Ida-Shekaresh bounds, this bound is basically, this is like at most k plus L to the 3/4 choose L to the 3/4. And that one is the same thing but with 2/3. And this is like k to the power L to the 3/4. That's like k to the power L to the 2/3. They're like nowhere near each other, even just when L goes to infinity slowly. Right? So we win by some large polynomial factor, even if L is tiny. If L is just like 10 to the 10, and k tends to infinity. Okay, and so this is just an upper bound, but the simple lower bound you get from taking a random coloring gives you basically the same behavior.
So here we
Yeah.
k greater than L. What is k much smaller than L?
Yeah, so we're not dealing with that. So yeah, by assumption from the beginning, k is bigger than L. Yeah, so I'm deliberately trying to find a book in the color that we're looking for the larger object. Yeah, yeah, and that's important because otherwise we couldn't really hope for this boost that we're getting, right? So, yeah. Yeah. Okay. Okay. Yeah, so I'll perhaps give a slightly more precise version or explain this a bit more. Or maybe I can do it now actually. So Yeah, because I want to make this a bit, I want to add another step here if possible. So I want to do this, and I want to take, I'm going to call it W of x, or omega of x, whichever you prefer, maximal. So subject to this condition. So what is this W of x? When you think about it as being sort of the weight of x, it's basically just going to be a measure of this thing. So in fact, why don't we just define for now, this is the weight of x. Okay?
Does the weight be greater than p minus alpha? Why do you want it to be greater than p minus something else?
So we haven't yet. So we it's going to be important that it's bigger than that this number here is much smaller than alpha, which is why I put k squared, because it's just that's already smaller than alpha, right? Yeah, that's all we need. Yeah, exactly. Yeah, so this thing will just be fighting with alpha. Okay. Okay. So this is basically red. I'll define this more precisely afterwards when we check that things work. So red density between, what am I saying, x and the red neighborhood of x and y. Okay. Okay, and go to step 4. Okay. Okay, so we chose central vertex, went to step 4. No other choice. Now we do a red step. If the red density between the red neighborhood of x in x and the red neighborhood of x in y is at least p minus alpha p. Okay, p minus alpha p. Then update A becomes A union x. B stays as it is. X becomes this guy. Y becomes this guy. Okay? Yeah, sorry. So if you look at yeah, maybe I should write it over here, I'm not quite sure. I kind of want to squeeze in. Can I get rid of the blue step? Or should I get rid of the picture?
Blue step.
The blue step, okay. never get rid of the picture, whatever happens. Okay. Right, so let's do 4 here again. So if yeah, so I think it's the easiest way to say it. The density of red edges between the sets, these guys, so the red neighborhood of x in x and the red neighborhood of x in y is at least p minus alpha of p. Then we update like this. Does it make sense? So this is the red neighborhood of x in x. This is the red neighborhood of x in y. He's interested in looking at all the edges here, what proportion are red. Right, that's the red density. Okay, and we update by adding x to A. B stays the same. X becomes this red neighborhood of x in x. And y becomes the red neighborhood of x in y. And go to step 1. Thank you. And go to step 1. Otherwise, go to step 5. Okay? Okay, so very simple. Just if this is good, then this is automatically good, this is automatically good, we can do a red step. We're happy. Otherwise, we're not happy, this density is too small, so then we have to do our density boost step. Yep.
Do we really need to assume that there is no red K or no KL, or you can just, okay, if we run this many red steps, for instance, we get a red K and we're done.
Right. So why is it useful that? So in the big blue step, it's going to be useful. There's no red KK. Because we're going to use this number of vertices to find our large blue book. We're going to use the fact we have Ramsey K versus L to the 2/3 of these vertices. Okay, it's going to be useful. It's also going to be useful to say that, okay, we don't have too many of these steps because this guy doesn't grow too much. But, right, the algorithm works anyway.
Okay, if we can't find this,
so you could,
we have this right click.
yeah. Right, you could say stop if you create a right click. Yeah, so if you don't like proofs by contradiction, then you can do that instead. Right. Fair enough. Okay, so 5, finally, we have this density boost step. So we arrived in step 5, so we already know that the density is at most this. And so there's no ifs. We just do this. Okay? Update. The steps as follows. So A stays as A. B gets the vertex X. Right? X becomes the blue neighborhood of X in X. And y becomes the red neighborhood of x in y. And go to step 1. Right, so what have we done? We've replaced x by this blue neighborhood. So we can put x in B. We've replaced y by this red neighborhood. So, which is fine, because we didn't put anything in A. Or sorry, we did fine because, but anyway, so the gain is we've got a boost in the density. The cost is that there's two costs. One is we've shrunk y, even without adding anything to A. So we've lost our dream of getting a book of size 2 to the minus t times n. Right? And this set might be super small. So we might have lost a lot of x.
Does it really matter that we add x to b on the density boost step?
Yeah, so good question. So yes, it does matter.
So there will be all of L density boost, all of L density boost steps. Or?
There will be order, yes, the number of density boost steps will be constant times k. Oh yeah, constant times L. There really will be a lot of them. If we didn't do this, then there could also be a lot of blue book steps, which would then shrink x by a lot. So it really matters in restricting the number of blue book steps and therefore the decrease in the size of x. But yeah, thank you. It's a very good point. It's an important point. Yeah. So in some other density boost ideas that we were using, we were not getting this benefit. So you need a much bigger density boost to compensate for that. We were hoping to get one, and one should be able to get one. But right. Here we can get away with a very small density boost because we're not losing so much. Okay.
Sorry, you were
Yeah.
discussing the loss of our dream of getting a...
Oh, right. Yeah. So, so our y in the end, how large will our y be in the end? So perhaps, yeah, that's the next thing to talk about. So let's say that there are t of these red steps and s density boost steps. Then what is the size of y at the end? Well, when does y change in the algorithm? Only when we take a red step, we go to the red neighborhood, or a density boost step, we go to the red neighborhood. Otherwise, it stays the same. And it goes down by a factor of, we will show, in the worst case, p0 minus little o1. So it's at least p0 minus little o1 to the s plus t times y. Okay? And y is going to be like n. Let's put n. Okay? So this is what we're fighting against. What we'd really like is have just t here. We don't like this s at all. This s is our loss in y. Fortunately, if mu is pretty small, our density boosts are pretty big, and therefore there should be a lot fewer density boosts than red steps. So the ratio of, we will show eventually that s is at most mu over 1 minus mu times t. Where this means, let me set up a little OK here. Okay, so this is going to be one of our main aims, is to prove this inequality.
And just to recap from Simon's,
Yeah.
this is just because we're capped at density at most 1.
Just because we're capped at density most 1, and we chose our alpha to be increasing exponentially, so we can't go up too many times. Or if we keep doing density boost steps, do too many extra density boost steps, we pretty quickly hit the boundary. So in only 1 over epsilon times log steps, we'll hit 1. Okay. So really this little OK, it's a 1 over epsilon from that. There's also some big blue steps you have to worry about, so those guys go in here, also a little OK. Right, just so other little things like that. But the main thing is this. Right, and so now you see if mu is small, and think of mu as gamma, so if gamma is small, s is much smaller than t. Which means actually here, we're getting pretty close to our p0 to the t that we wanted. Right, so the smaller gamma is, the smaller the loss is in this inequality. So that's sort of, roughly speaking, why we're winning more off the diagonal. Okay. Oh, wow. That took a lot longer than expected. Okay, so at least we've seen the algorithm now. Okay, so in the rest of today, I'd like to start filling in some of these details of how we do this. No, but before doing that, I'd like to state one more inequality. So, right. Right, so maybe I'll put those things over here. So the 3 lemmas that we can try and prove are as follows. So we're going to try and prove this bound on y. Okay. T equals number of red steps. S equals number of density boost steps. Right. Okay, that one's pretty simple, right? We just need to make sure we control P. Huh?
Yeah, but we always have to ensure that it's P0 instead of whatever P we would get. Right, this is a small detail, and it's not actually N, it's probably N over 2.
Yeah, right. But there's a little O1 here, right? So,
Okay,
yeah. Yeah, so really there's a 2 to the little OK in front. So I don't, maybe, yeah, so I could write this as 2 to the little OK times P0 to these things. But yeah, so we have to prove this. We have to make sure we don't go too far below P0. Right. Okay. We also want to bound on X. So what is going to be our bound on X? So when does X decrease? Tell me ways in which X decreases. This is probably a good thing just to talk through this inequality to just think about what happened in the algorithm. So when does X change? Say again? Yeah. So let's do what should we do first? Yeah. Let's do red step because they're easiest. Yeah. So the red step's very easy, right? You go down by at most a factor of with 1 minus mu. So you at least 1 minus mu, and there's t of them. So that's super easy. You get a 1 minus mu to the t. Okay, great. There's going to be n at the end. So, yeah, when else does it go down? In a blue step. So what happens in a blue step? Yeah, so what happens to X?
Mu to the power size of S over 2.
Yeah, forget the over 2. Yeah, mu to the size of S. Exactly. You put for each vertex you put in here, you lose a factor of mu. You have at most L here, so you lose a mu to the L. Okay. There's a mu to the L. Okay. When else does it go down? In the density boost, exactly. And then what happens? So that's a bit more scary, right? Because this has size at most mu. So let's pretend, for now, that every time this happens, let's introduce a new letter. Let's say instead of going down by mu, it goes down by beta. Okay, beta's at most mu, right? So we've already paid a mu for each of these steps. We need to pay an extra beta over mu to the s. Okay, so here I'm pretending.
Oh, right.
Pretend. The size, the blue neighborhood of x, intersection x, is beta times x for all density boost steps. So, okay, we're not really going to assume this in the proof, but let's pretend it for now. But it's not such a weird assumption, because it's not so hard to convince yourself that the worst case should be, whatever the worst beta is, you should always do that. So it's not obvious, but why would you vary the size of this set by factors in, like sometimes take mu, sometimes take mu over 2. I mean, so okay, what's the reason? The reason you're getting a larger density boost that way. So there's some convexity argument, which is literally just the AMGM inequality. So we will make crucial use of the AMGM inequality to tell ourselves that actually we can basically so what we're really going to define beta to be is the harmonic mean of the betas that we get in each of the density boost steps, except we're going to not include the very large density boost steps. We're going to deal with them separately. So the actual definition of beta is that. It's the harmonic mean of the betas over reasonable sized density boost steps. Okay? But for now, let's just pretend it's always beta. Right? Okay. Okay. And it's very easy. And what else? Yeah, so there's also degree of regularization. We're going to show that they don't matter much. Choose little OK. Okay? So by our choice of 1 over root epsilon times alpha, the fact that epsilon is small, so we're allowing a big decrease, means that actually the total effect of those will be small. Okay? Because if you lost too much volume of x in those steps, your density would go up way too much.
This is not really true, right? This is 1/2 to the OK.
Yeah, sorry. So little OK is absolute value. So this is a negative number whose absolute value is little OK. Yeah. Times n. Okay? And that's we're going to prove that lemma. Okay? Okay, where beta is this funny thing, so perhaps I'll just write it. So beta is defined to be 1 over the size of S star sum of, 1 over beta, sum of 1 over beta I in S star, where n bx intersect x equals beta I times x for each density boost step, and S star is the set of moderate density boost steps. Which just means not crazily large, right? So the big ones, there'll be very few big ones because there just isn't space for them, and they just help us. But in the calculation, if you do it with those, then it messes up. So you have to treat them separately. But it's just a silly technicality. Okay. Okay. So it's basically just the average. Okay. Right. And the third final lemma. Get rid of this. Right, so with this bound on S that we have, except actually we get something a bit better, because our density boost step, when we do a density boost step, this is no longer mu, this is beta. Okay, so instead of mu, we get a beta.
There's some delicate interplay here between how we use beta and this large.
Yeah, so what is the worst value of beta? It's not really obvious, is it? Yeah, and actually if you put it in a computer, it turns out that it's not mu, and it's not something much smaller than mu. It just hovers like 80% of mu or something. It really hurts you here, taking beta. So the smaller you take beta, the smaller x is, and therefore the smaller t is. Right? Your algorithm ends early. So you take beta smaller, then t is smaller. But beta smaller means s is smaller. So here, you get a better bound on y. So when beta's smaller, a gets smaller, but y gets bigger. And y is fighting against some weird, crazy function here, nonlinear function. And you have to balance these two things out. So we don't balance these things out. We have to deal with whatever it gives us. We show whatever beta the enemy chooses, the corresponding s and t are good enough to beat this. Okay. So what you actually end up getting, maybe I can draw this picture now. Yeah, perhaps this is a good time. So here is a picture of t and s that are given to you by the algorithm. Basically all you have are these three bounds, right? These three things tell you what's going to happen in the algorithm. Okay, this is all we need to prove. We've almost already proved it, right? I mean, okay, there's some checking. But once you've got these three lemmas, then when you check in a computer, what you see is the algorithm will end in this region here, which I'll color in blue, just to match the paper. Okay. So you know you're going to end over here somewhere, right? But you don't know where. The enemy chooses. And then you can also draw, so the smaller t is, and the bigger s is, the worse it is for you in trying to beat this guy. Right? So up in this corner is very bad for you. Down in that corner is great. Okay? So you can also plot the region like this, in which your bound is not strong enough. So the blue is you.
What is the scale of this picture?
Yeah. So this is k, 0 to k, and 0 to really it's like 0.7 k or something, 2k over 3, something like that. Sorry, this is a picture in the diagonal setting, right? So yeah, so what is this picture? The blue is where these three inequalities guarantee you're going to end up. You don't know where, but you can guarantee you end up somewhere in the blue, right? Right? Because whatever beta the enemy gives you, that corresponds to a certain size of t for a particular mu. So this is a picture with mu equals, as it turns out, 2/5.
It doesn't depend on gamma or...
Sorry, this is for diagonal. This is gamma as a half. So this picture is, yeah. Sometimes I'll draw a few pictures just to compare. So it turns out that when gamma's a half, so what mu do you want to take? So I've given it away, but at least we can start thinking about it. Like, do you want to take mu equals a half when gamma's a half? Not really, because all you know about beta is at most mu, right? And the beta is at most mu. So if mu is a half, beta could be a half, s could be as big as t, and then you just lost everything, right? A half to the 2k is the end of the world, right? So you need to take mu a bit smaller than a half.
Isn't the intuition of taking mu smaller than a half the fact that we are looking at something that is asymmetrical? We are looking for a radical regardless of...
Right, so yes, yeah.
Intuition of, but it's not that simple, right?
Right, so I think the fact that we're doing something asymmetric means that we shouldn't just assume that it's a half. Yeah, absolutely, right. Yeah, so we're allowed to take mu a bit smaller because we're not symmetric, whatever, so it makes sense to. We lose something here, right? But we gain a bit here to compensate, right? Okay. And then we gain a bunch here, which compensates more. It turns out actually the value of mu you take is also you have some flexibility. It doesn't really matter if you take it to be 0.41 or 0.39, and so we just pick 2/5 because it's a nice number, right? So yeah, anything in that range will give you a similar picture. For this diagonal, it'll give you something where the blue and the red overlap by a little bit, right? Okay. So sadly, this is the red. This red corresponds to Edis-Shekerash, right? So this is taking k minus t plus L, choose L as your bound and your Ramsey number. Right, so in fact, I should say y at the end is at least is less than this. This is the red region. So the red is the bad region, where you have failed to prove what you want. Yeah.
And
Yes.
It actually means there's a choice of beta such that
Yeah.
you get...
Exactly. That the enemy can choose a beta such that we end up here. So it's in the blue, so it satisfies all the inequalities, but we're still in the red, and so it's not enough to apply Edis-Shekerash. Right. However, we draw another picture. If you take gamma smaller,
Why do you apply Edis-Shekerash but not induction here?
Right. So, I mean, yes, we do apply induction. that's the, yeah. Yeah, so maybe I'll put this over here in this new slide. Yeah, so at this point we hadn't proved anything, but right, okay. Yeah. So again, so I'll do this t again, and this s. So now if, say, gamma is, like, I don't know, like a fifth or something a bit smaller, then you draw the same picture, and you end up with two sets that happily don't intersect. Right. This is again with, this is a picture of y less than k minus t plus l, choose L. And this is where you end up. Okay? So just having proved these three lemmas, some very, very simple analysis from this point, very simple, just playing, I mean, or sticking in a computer if you like, or whatever, gives you that you are guaranteed to end in the blue set, and that the red, the dangerous set is disjoint. So therefore, you can exchange this. So you then make, so if you make y a little bit smaller, minus delta times k or whatever, then this set gets bigger, right? If you make y a bit smaller, sorry, what am I talking about? What am I talking about? Sorry, you can allow y to be a little bit bigger. What am I saying? Sorry. It's the other way around. So I should say this properly. So what is the definition of the red? The red set says if n equals k plus L, choose L, then y is less than k minus t plus L, choose L. Sorry. Right. Okay? So that's what the definition of the red set is in this picture. Okay, let's just take a second to make sure everyone's happy with the definition. Does it make sense? Okay, so what is your final set?
It doesn't depend on S.
It depends on n, obviously. So it depends on s as well, of course. So, but yeah, what do you want? So your final set, y, is n times all the stuff you lost. Right? So for a given value of s and t, so here's a value of s and a value of t, right? Then, and a given value of p0. So I guess I'm also assuming that, let's say, p0 is 1 minus gamma here. Right? Let's assume that the initial density is what you think it should be. Okay. So for a given value of t and s and p0, you can see what y is. It's right there, right? And you can ask, is that number, that bound on y, is it bigger than this guy?
So we could have written this as, instead of size of y, is 0 minus the 1 of s plus t n.
Yeah, right.
Because this is a lower bound of y. Right? This
Yeah,
is
so if you like, so this, yeah, the boundary is, yeah, exactly. So it's p0 to the s plus t, so 1 minus gamma to the s plus t, times n is less than, thank you, k minus t plus L, choose L. Right? Okay. So if we decrease n by a bit, the red set gets bigger. Okay, now it's the right way around. So we can decrease it until they basically touch. And that's the moment at which, so sorry, slight problem. This one is also moving. So actually they're both moving. Both lines are moving as you decrease n. So if you decrease n, this one gets a bit bigger, this one gets a bit smaller, sorry, they both get a bit bigger. At the moment when they touch, that's the value of n that you've got, that you've proved. That's the n that the bound on the Ramsey number that you've proved is the moment at which they touch. Not exactly, because I'm assuming this, but basically, yeah.
Why at the moment they touch is the boundary?
Because that's the moment at which the blue set that you're guaranteed to be in is no longer enough to beat the Edge-Zekerish bound without without iterating the argument.
Okay.
Yeah, so right, you can iterate the argument, and it gains you something, but it gains you actually less than you might think. So, so one problem with iterating the argument is this thing really stops being true. Yeah. So, yeah. So it gains you a little bit, and crucially, it gives you enough to beat the diagonal, but only a little bit. Okay. So what does this argument say? So what's the conclusion of this? Does this make sense or not? I want this picture to make sense. I think it's important for us to understand what this picture is saying. So the blue set is, right, so it's where you're guaranteed to end up. So,
There exists a sequence of bits such that the algorithm ends with that bound, right?
yeah, so
Fix the value of n. Shouldn't the pictures be different for different values of n?
they are, yeah.
But then why do we write that n is equal to
Ah.
something?
Sorry, so I confused you with that. So right, so yeah. Okay. So given n and p0, right, and mu and whatever, then we can define the red and blue sets, right? So the blue set is where we know we end up. So the pair ST that we're given by the algorithm, when at the point where X disappears, we don't get to choose exactly what T is or what S is, but we know it'll be somewhere in the blue set. The red set corresponds to 1 minus gamma to the S plus T times N is at most, right, whatever bound on the Ramsey number that we have, basically. But let's just use for now the Eddy-Zekerish bound. Okay. And right, as you say, so both these sets depend on n. Right? So how do we know we end up here? This is, we just get this from this, this inequality. Right? So it's basically the point at which this thing is 2 to the little OK. So all of this thing is 1. That tells you that S and T gives you some relation on S and T, right?
At this point, I'm just going to confirm something.
Yeah.
N is the Ramsey number you get in the end, right?
Right. So I mean, in the algorithm, n is just however many vertices you started with. So the bound on the Ramsey number you get is the minimum n such that these two sets are disjoint, for which you can choose a value of mu such that they're disjoint for, yeah, so I'm cheating here, right? For any p0, right? Yeah, so I'm cheating at this point. Yeah, right. So it turns out not to be too difficult to fix, but right. But yes, you lose something. You lose something. Okay. Yeah, so I guess if instead of doing the Ramsey number, we were doing the Ramsey number for colorings with a given initial density of red edges, then it would be exactly this, right? Yeah. Yeah, so the blue set is whatever the beta that you get, you know you're going to end up, this line, points to this line corresponds to different values of beta. Right, so each value of beta gives you, via this inequality, right? So this blue line corresponds basically to this line here is 1 minus mu to the t, mu to the L, beta over mu to the S equals 1. Times n equals 1, basically. Right. And the little OK is, I mean, it's a strip that you can't see because it's not at this, it's a lower scale than this picture. Right. Right. So this corresponds to, for each value of beta, you get a sort of a point on this line.
Why it's clear that the intersection point is the best one?
So the intersection is the worst one, right?
Yeah.
If they intersect, then we cannot guarantee we win.
No, yeah, but I'm saying in the limits when you.
Oh, I see. I mean, so the point is, as you decrease n, this set increases in size. This set also increases in size. And the moment that they intersect, then you've lost. Then you can no longer guarantee you find a big enough book. Right? So then you have to stop. Then okay, your n is shrunk too much. You haven't won. Yeah, exactly. Yeah. So they're both sets are growing as you decrease n. Yeah. Okay. Okay. So basically, the only thing we have to do is prove these three lemmas. Right. Which the first one it will involve bounding p. Yeah. So that'll be the main challenge.
So we don't have to worry about the graph having different density than we expect.
Oh yeah, so then we'll have to worry about that. But it's a no. So that's just really you just pre-process a little bit. It's very easy. Yeah. I mean everything's very easy, but that is particularly easy. Right. So I promised you, and I have 10 minutes left. I promised you the proof of that we'd find a big blue book. So let's do that. Okay. So maybe I'll do it. Okay, yeah, I guess. Did anyone manage to prove the lemma? I think you'll be surprised. It's very simple. So lemma, if there are at least Ramsey k L to the 2/3 vertices in X with at least mu x blue neighbors, then either X contains a red KK or X contains a blue book ST such that S has size at least L to the 1/4 and T has size at least mu to the S times X over 2. Okay. Maybe I'll leave those up. Yeah, look at that. Okay, so proof. Okay, so we have this big set of vertices. Maybe call it W. These are the vertices of high blue degree. High blue degree. Okay, and it's at least Ramsey k L to the 2/3. So either there's a red KK, or there's a blue clique U of size L to the 2/3. Okay. Right, so we're going to assume the latter. And everyone in U has at least mu times x blue neighbors out. So let's look at the rest of the world. This is U complement, or x minus U. Everyone here.
X minus U or X minus W?
Yeah, I'm going to throw W in here. So I've drawn it twice, but you can perhaps forgive me. Okay, so everyone in U has this many, and U is tiny compared to X, right? X is like Ramsey k L to the 3/4, and U is nothing. Okay, so basically this is the whole thing. Okay, so basically all of these guys are here.
Maybe we have other neighbors who are smaller than.
Very few, yeah. So it's minus size of U, but this is tiny compared to this guy, because this is like Ramsey k L to the 3/4, and this is L to the 2/3. Okay, so I'm just going to ignore this. Okay, so the density of blue edges here, density of blue edges is basically mu. Right? Okay. So now what should we do? So we want to find, let's call this number B. I want to find a set B, a set of B vertices inside here. I'm going to call it S, such that their common neighborhood down here is as big as you'd expect for a random set S of that size. So how should you choose S? So randomly, right? It's actually even easier than to invent a random choice, right? It's like, yeah. Yeah, so if L is very small, instead use dependent random choice. But when L is big, just literally pick it randomly, look at the expected size of the common neighborhood, and it's that. That's it. That's the proof. Right? So expected, so S is random B subset of U, the expected size of the common blue neighborhood of S is at least mu to the size of S, mu to the B, times size of X over 2. And you're a tiny calculation. Do you want me to do the tiny calculation? I guess I can do it. I guess use convexity. I've got still got 5 minutes, got ages. That's forever for this proof. I'm learning Brazilian style. Right, what are we doing? So let's say Z is the size of this thing. So NBS is the intersection of the blue neighborhoods of V and S. Right. So expected value of Z equals, so 1 over size of U, choose B. I'm going to call the size of U M. i times the sum over vertices of x minus u of the size of the neighborhood, blue neighborhood of v in u, choose b. Right? Each vertex outside, here's u, each vertex outside has some neighborhood. When is this guy in the common neighborhood? When you choose S inside here. Okay? So this probability of being chosen is this divided by that. Is that okay? Right, of all of the M choose B sets you could choose, you had to choose one inside his neighborhood. Okay? Convexity. At least. M choose B to the minus 1. How big is this guy on average? It's mu times M. Mu times M choose B. Now this makes sense as long as mu times M is bigger than B. Mu is a constant. M is L to the 2/3. B is L to the 1/4. So we are super happy. Times size of x minus u. Right. And then, okay, now we just have to compare two binomial coefficients. So maybe you just believe me when I tell you that this is like mu to the b, and then there's like an e to the minus, it's like b squared over m or something. Maybe there's a constant factor somewhere. Who cares? And times size of x, because this is like, okay, over 2, whatever. Okay? Okay? And this thing, okay, maybe I'll do this over, yeah, whatever. Okay, over 2, I'll prove over 4. B squared over m is very close to 0, so this is very close to 1. So this is at least mu to the b size of x over 4. Okay. And that's it. Exercise. Use this lemma to deduce the following corollary. If the initial density of red edges, so if n equals 4 minus epsilon to the k, and chi is a red-blue coloring, and the density of red in chi is at least a half plus delta, so it's not a half, then there exists a monochromatic kk. Sorry, you have to pick epsilon and delta correctly, but okay, for every delta, there's an epsilon. I think it gives like delta to the 4 or something. Maybe delta squared, I forgot. Not enough to deduce anything with, but anyway. So this is like a, so Erlich and Semerady proved that if the density of red is very close to 1, then you get a big exponential improvement in Ramsey. So this tells you if you have a small improvement in the density, you get a small improvement. And it follows very easily from this lemma. Yeah, but proof exercise. Perfect timing. Okay.
This is for the diagonal case, like.
Yeah, also for off diagonal. Yeah, if you're far from if your density is far from gamma, so 1 minus gamma plus delta, yeah, you'll get the same thing. Yeah. Yeah. So basically, you just find use this lemma. Sorry, it's not a corollary of this statement, because I'm doing this with L to the quarter. It's a corollary of the proof. So I use the same proof. So remember about exercise instead. Exercise. There's exercise twice, but whatever. Yeah, use it. So you use the same proof, find a big book, get a small improvement. More questions? No? Okay, so we carry on Wednesday. Yeah, so on Wednesday I'll attempt to prove these three lemmas. And then maybe next Friday I'll talk a bit more about how you then actually go about deducing the bounds in the end. And there's two different ways, in fact, that we get the two different proofs of the improvement on diagonal, and so I'll try and explain both of them. Okay, cool. Okay.